Ever feel like you're just drowning in information when you want to understand something new? You know, that feeling of trying to drink from a fire hose.
Oh, absolutely. Mountains of articles, complex papers.
Yeah.
It can be overwhelming.
Well, today on the deep dive, we've waded through it for you. We're tackling the basics of computer programming and then diving into the really fascinating world of voice cloning and text-to-speech.
Yeah, it's quite a mix. We looked at an article on programming fundamentals, a research paper on real-time voice cloning, a Reddit discussion about building TTS AI.
Plus the Wikipedia page on speech synthesis, reading rockets on TTS as assistive tech, and an article from Fleeky looking at the future. Quite the stack.
It is.
So our mission today, basically pull out the core programming concepts you need to kind of grasp how AI voices work, and then explore where we are now and where we might be heading with making machines talk.
Sounds good. It really connects, doesn't it? How these fundamental logic steps in programming eventually lead to something as complex and human-like as speech synthesis.
Exactly. So let's start right there. Computer programming. Lay it out for us. What is it at its most basic level?
Okay, so a computer, fundamentally it's an electronic machine, right? Takes input, processes it based on instructions, and gives you an output. The key thing is it's programmable.
Meaning we tell it what to do.
Precisely. And the basic parts are the input unit, like your keyboard or mouse, then the CPU, the central processing unit, that's the brain.
And inside the CPU.
You've got the ALU, the arithmetic logic unit, doing the math and comparisons, the control unit managing the flow, and memory to hold data temporarily while it's working. Then finally the output unit, screen, speakers, whatever.
Input, process, output. Got it. You mentioned instructions. Is that the program, the code?
Exactly. A program or code is just a set of step-by-step instructions. A procedure, really. You give it to the computer to do a specific task.
Like a recipe.
Perfect analogy. If you want to, say, calculate the average of a bunch of numbers, you don't do it by hand. You write a program. Step 1, get the numbers. Step 2, add them up. Step 3, count how many numbers. Step 4, divide the sum by the count. That's the program.
And to handle those numbers or any information, we use variables.
Yes, variables, think of them as labeled boxes, containers. You put data in them, a number, a word, whatever, and the label lets you find it again.
Are there rules for the labels?
Yep, usually alphanumeric, sometimes with underscores or dollar signs. Generally got to start with a letter. When you declare a variable, you're telling the computer, hey, set aside a spot in memory for this kind of data and call it this.
Okay, so we have instructions, variables. How does the computer actually understand what we've written? Is that the syntax part?
That's syntax. It's like grammar for programming languages. A set of strict rules defining how instructions must be structured so the computer can interpret them correctly.
Can you give an example?
Sure. In many languages, like Java or C++, to store the number 10 in a variable called a, you might write int 10. The int says it's an integer, a is the name, assigns the value, 10 is the value, and that semicolon often marks the end of the instruction. That's all syntax.
Right. And you mentioned int for integer. That brings us to data types, doesn't it? What kinds of data can these variables hold?
Good question. Data types specify what kind of value a variable can hold and what operations you can perform on it. There are basic or primitive types built into most languages.
Like int.
Exactly. Int for whole numbers, short and long for smaller or larger whole numbers, float and double for numbers with decimal points, Boolean for true-false values, char for single characters.
And non-primitive.
Those are usually more complex, often built from the primitive types. Things like string for sequences of characters, like text arrays for lists of items, and in object-oriented programming, class and interface, which are like blueprints for creating more complex data structures.
Okay, so we have instructions and data. How do we control the order things happen in? Make decisions, repeat things.
That's flow control. It dictates the execution sequence. The simplest is sequential flow, just line after line, like reading a recipe straight through.
Makes sense.
Then you have selection. That's making decisions, usually using if statements. If this condition is true, do this block of code. Otherwise, maybe do something else.
Like choosing a path.
Exactly. And finally, iteration, or loops. This is for repeating actions. You have for loops, while loops, do while loops. You basically say, keep doing this block of code until this condition is no longer true. Very powerful for processing lists of data, for instance.
So we're building up this logic step by step, but why can't we just tell the computer what to do in plain English? Why all these specific languages, C++, Python, Java?
That's the core reason programming languages exist. Computers, at their heart, only understand machine language binary code, ones and zeros representing electrical signals. It's incredibly low level and tedious for humans. We humans use natural language, which is rich, flexible, but also ambiguous. Computers need absolute precision. So, programming languages are the bridge. They let us write instructions in a structured way that's closer to human thought, but can be reliably translated into the machine code the computer actually executes.
And I noticed there seem to be different styles or methods of programming. Monolithic, modular, object-oriented.
Yeah, those are different ways to organize the code, especially as programs get bigger. Monolithic was kind of the early way, everything in one giant file. Gets messy fast.
I can imagine.
Modular or procedural programming broke things down. You create separate reusable functions or procedures for specific tasks. Data and functions were often kept separate, though.
And object-oriented, OOP.
OOP takes it further. It bundles data and the functions that operate on that data together into objects based on templates called classes. It helps model real-world things better and encourages organization, reusability, and makes maintaining complex software easier. The core logic might be similar, but the structure is very different.
Before you even write the code in a specific language, there's the planning stage, right? Algorithms, pseudocode.
Absolutely critical. An algorithm is the abstract, step-by-step procedure for solving the problem. It's the logical plan.
Like the average calculation steps you mentioned earlier?
Exactly. And pseudocode is a way to write down that algorithm using informal, English-like statements before you commit to a specific programming language's syntax. It helps you think through the logic. For the average, start. Get list of numbers, set sum 0, set count equal number of items in list, loop through each number, add number to sum, end loop, calculate average equals sum count, display average, stop, something like that.
It makes the logic clear without worrying about semicolons yet.
Precisely. Then you translate that pseudocode into, say, Python or Java.
Speaking of which, there are so many languages. C, C++, Java, JavaScript, Python, Swift, R. Where does someone even start?
It can seem daunting. CC+ are powerful but complex. Java is widely used in enterprises. JavaScript is essential for web development. Python is hugely popular, often recommended for beginners due to its readability, and heavily used in AI and data science. Kotlin and Swift are big in mobile app development. R for statistics, Ruby, Scala, TypeScript. The list goes on.
So, advice for beginner.
Focus on one language first. Get the fundamentals down, variables, control flow, data structures. Python's often a good starting point. Once you understand the core concepts, learning another language becomes much easier.
And why bother? It seems like a lot of effort. What are the payoffs of learning to program?
Oh, huge payoffs. It unleashes creativity, building websites, apps, games. It fundamentally changes how you think, promoting structured, logical reasoning. You learn to break down complex problems and approach them systematically.
Improves problem-solving skills, then.
Definitely. You look at problems from different angles. Plus, the career opportunities are vast across almost every industry now. And it's very hands-on. You learn by doing, building things, maybe even competing in coding challenges. It's a powerful skill set.
Okay, that programming foundation is super helpful. Now let's pivot to how that connects to making machines talk. Speech synthesis. What exactly is that?
Speech synthesis is basically the artificial production of human speech.
Yeah.
The tool that does this, hardware or software, is a speech synthesizer.
And text-to-speech, TTS, is a type of that.
Yes. TTS specifically converts normal written text into spoken words. It's distinct from systems that might need phonetic input. And of course, it's the opposite of speech recognition, which turns speech into text.
So how does a TTS system actually take, say, this sentence and turn it into audio? What happens inside?
Generally, there are two main parts, the front end and the back end, or synthesizer.
Front end.
The front end takes the raw text and processes it. It does text normalization, figuring out how to say numbers, abbreviations, handling punctuation. Then, crucially, it converts the words into phonemes, the basic sound units of the language. It also analyzes the text for prosody, the rhythm, stress, intonation marking phrases, and sentence boundaries.
So it figures out what sounds to make and how they should sound.
Pretty much. Then the back end, the synthesizer, takes that linguistic representation, the phonemes and prosody information, and generates the actual audible sound wave.
Fascinating. How long has this tech been around? Was it always this good?
Oh, the idea is quite old, with early mechanical attempts centuries ago. Electronically, things like the vocoder in the 1930s were early steps. But maybe the most famous early consumer example was the Texas Instrument Speak and Spell toy from the late 70s.
I remember those. Kind of robotic sounding, though.
Exactly. Early synthesis was often very robotic. The quality, the naturalness has improved dramatically over the decades.
Which brings us to quality. What makes a TTS voice good?
The two big measures are naturalness, how much it sounds like a real human, and intelligibility, how easy it is to understand. You want both, ideally.
And how do they actually create the sound? I read about concatenative informant synthesis.
Right. Those are two major historical approaches. Concatenative synthesis works by using pre-recorded snippets of human speech.
Like cutting and pasting audio clips.
Sort of. It could be tiny sounds, diphones, syllables, or even whole words or phrases. These are then strung together, concatenated, to form the desired utterance. Because it uses real recordings, it can sound very natural.
What are the different types?
Well, unit selection uses a huge database of varied recordings and picks the best segments, potentially very natural, but needs tons of data. Diphone synthesis uses units covering the transition between two sounds, smaller database, less glitchy perhaps, but maybe less natural overall, and it's declining. Then there's domain-specific synthesis for limited contexts, like automated phone systems or announcements, using whole recorded words or phrases. Very natural for what it does, but obviously limited.
Any downsides to concatenative?
Sometimes you can hear glitches or slight unnaturalness where the pieces are joined, especially with unit selection if the perfect segment isn't found.
Okay, and formant synthesis. How is that different?
Formant synthesis doesn't use any human speech samples during the actual synthesis. Instead, it creates sound from scratch using an acoustic model, essentially a mathematical model of the human vocal tract.
So it's purely synthetic.
Yes. It generates sounds based on controlling parameters like formant frequencies, key resonances of the vocal tract, and amplitude. Historically, it often sounded more robotic, but could be very intelligible even when sped up.
Advantages.
The programs are much smaller, no massive audio database needed, and you often have very fine-grained control over prosody pitch, speed, etc. The speak and spell voice. That was formant synthesis. Same for many early Atari game voices.
And now, deep learning seems to be the big thing.
Absolutely. Deep learning using artificial neural networks trained on vast amounts of audio data has revolutionized TTS in recent years. This is where the real breakthroughs in naturalness are happening. Models like 15.ai showed impressive multi-speaker capability and emotional range. And companies like 11 Labs are pushing the boundaries of lifelike, emotionally nuanced speech generation in multiple languages.
Is it perfect now?
It's getting incredibly close to human naturalness.
Yeah.
But challenges remain, needing huge data sets for training. Sometimes controlling specific aspects of the output can be tricky, ensuring consistency.
And this ties into voice cloning or audio deepfakes.
Exactly. Voice cloning is a direct application of this powerful AI. It aims to mimic a specific person's voice, their tone, cadence, style, often trained on just a small sample of their speech. It can synthesize phrases they never actually said.
Which sounds potentially useful.
Oh, definitely. Think personalized audiobooks read in a loved one's voice, better voice assistants, accessibility tools, huge positive potential.
But also risky.
Very risky. The potential for misuse is significant. Creating fake audio of politicians or public figures, scams, bypassing voice-based security systems. We saw demonstrations where the tools like 11 Labs could be used for such things quite easily. It's a major ethical consideration alongside the technological advancement.
Right. So let's dig into the practicalities. That research paper talked about real-time voice cloning. What's the core goal there, technically speaking?
The main aim of voice cloning is to use machine learning models trained on someone's voice recordings to replicate their vocal characteristics, the pitch, timbre, speaking style. It's not necessarily about copying the underlying code perfectly, but about generating speech that sounds functionally identical, or at least very convincingly similar to the target speaker.
And the real-time aspect is important.
Hugely important. The research highlighted systems that can do this cloning quickly without needing hours and hours of the target voice. Maybe just a few seconds or minutes of audio that makes it much more accessible and, well, faster.
The paper had a diagram showing the architecture. Can you walk us through that? How does it go from a voice sample and text to cloned speech?
Sure. It's typically a pipeline. First, you have a speaker encoder. You feed it a short audio clip, the reference waveform, from the person whose voice you want to clone.
Okay.
The speaker encoder processes this clip and outputs a speaker embedding. You can think of this embedding as a compact numerical representation, like a digital fingerprint, capturing the unique qualities of that voice.
Got it. The voice fingerprint. What next?
That embedding then goes into the synthesizer module, along with the text you want spoken. The synthesizer itself often has several parts. An encoder processes the input text, turning it into some internal representation, maybe based on phonemes or characters.
Right.
Then, often using something called an attention mechanism, The model learns to align the text representation with the speaker embedding over time. This helps ensure the right voice characteristics are applied to the right parts of the text. Finally, a decoder takes all this information and predicts a MEL spectrogram.
A MEL spectrogram, what's that?
It's a way of visualizing sound, showing the intensity of different frequencies over time. It's like a detailed blueprint for the sound, capturing pitch, timbre, and timing tailored to the cloned voice.
Almost there. How does that become actual sound?
That's the last step. The vocoder. The vocoder takes the MEL spectrogram generated by the synthesizer and converts it back into an actual audible waveform, the sound file you can play and hear. The paper also mentioned RNNs, recurrent neural networks, are often used in these models because they're good at handling sequential data like speech and text.
That clarifies the process. Now, that Reddit thread was interesting, someone wanting to build their own TTS with voice morphing. What was the vibe there?
Yeah, the user wanted to input text, upload a voice sample, get the text spoken in that voice, and even tweak the voice. The general consensus was, yes, it's possible, but it's hard.
Not a weekend project.
Definitely not for a beginner. It requires significant machine learning knowledge, lots of data potentially, powerful computers for training. The advice was mostly look into using existing pre-trained models like Tortoise TTS or APIs from services like 11 Labs. They've already done the heavy lifting.
Which kind of loops back to the research paper's goal, right? They wanted to combine voice cloning and TTS.
Exactly. They were essentially trying to build that system the Reddit user described. They evaluated different approaches and found that a specific architecture, known as SV2TTS, speaker verification in text-to-speech, met their requirements for taking text and a voice sample and generating speech in that voice.
And they mentioned ethics, too.
Yes, they explicitly acknowledged the potential for misuse alongside the advancements. Their future work aimed at improving quality handling accents better, using more diverse data sets, but also efficiency, like reducing processing time and storage needs and boosting the overall accuracy of the voice clone.
Okay, let's broaden out again. Beyond cloning, TTS has major real-world uses. Reading Rockets framed it as assistive technology. How does it help people?
It's incredibly valuable for anyone with reading difficulties, whether that's decoding words, understanding text, or even issues with writing and editing. Having text read aloud can make a huge difference.
Okay.
It can also help with focus.
So it lowers barriers to accessing information.
Absolutely.
Yeah.
And when you combine TTS with OCR, optical character recognition, you can even have it read text from images or printed documents. It creates this multisensory experience, seeing the words and hearing them, which really aids comprehension for many people.
And looking forward, that Flicky article suggested some perhaps less obvious applications.
Yeah, some really interesting ideas there. Singing TTS, imagine AI generating realistic singing voices for music production. That could be transformative.
Wow. What else?
Language learning, using high-quality TTS to practice pronunciation and intonation in different languages. Marketing, creating personalized, engaging audio ads or messages at scale. And content creation, faster, cheaper audio production for videos, podcast, e-learning, especially helpful for creators who might have physical limitations preventing them from recording themselves.
So, summing up the pros. Definitely accessibility and savings in time and cost for content creators.
Those are big ones, yes.
But it's not all solved, right? What are the persistent challenges in speech synthesis? The Wikipedia article mentioned a few.
No, it's still an active area of research. Text normalization is still tricky. Think about homographs, words spelled the same but pronounced differently based on context, like read present tense versus read past tense, or how to pronounce numbers, dates, abbreviations correctly. Saint could be saint or street.
Getting the pronunciation right for every word.
That's the text-to-phone conversion challenge. Do you use a massive dictionary? What about new words or names? Do you use rule-based systems? Both have limitations.
How do you even measure if one TTS is better than another?
That's another challenge evaluation.
Yeah.
There's no single perfect objective metric. Listening tests are common, but subjective and time-consuming.
And the sound itself, making it sound natural.
That's prosody and emotional content. Getting the rhythm, the pauses, the intonation right, making a question sound like a question, conveying excitement or sadness. It's incredibly subtle. Research even shows listeners can tell if a speaker is smiling just from their voice. Replicating all that is still the frontier.
Wow. So much goes into just sounding human. Okay, as we wrap up this deep dive, what are the main takeaways you think folks should keep in mind?
Well, I think first is understanding that even complex AI like speech synthesis rests on those fundamental computer programming principles, logic, data, algorithms. Second, the progress in speech synthesis, especially with deep learning, has been phenomenal, leading to capabilities like voice cloning that were science fiction not long ago.
Yeah, the pace is incredible.
Third, the applications are already widespread, especially in accessibility, and they're poised to expand dramatically into creative fields, education, communication. And finally, we absolutely have to keep the ethical considerations front and center as this tech becomes more powerful and accessible.
It really has been a journey, from basic code logic to these incredibly sophisticated synthetic voices. It definitely leaves you with a lot to chew on.
It does. And perhaps a final thought for you, the listener. As these voice cloning tools get better and easier to use, what does that mean for us? Consider both the amazing potential for creativity, for connection, for accessibility, and the undeniable risks of deception and misuse. How do you think this technology will change how we interact online, how we consume news, how we trust what we hear? It's something we'll all need to navigate.
A really important point to ponder. Definitely encourages exploring some of these tools and research areas further.